Good afternoon, everyone. How are we doing? Can you all hear me? Huh? Yeah. So what I would appreciate, if you don't mind, I'm just getting set up here. If you could, if you're able to, turn on your cameras so we make this a little bit more. Okay. Would that be possible? Okay. So many responses. I'll give it a few minutes since we haven't yet started. Okay, everyone. Can you hear me okay? I can't hear anyone there, so please that we're there. Yes, wonderful. Thank you, Ivy. That's great. Wonderful. Brilliant. Okay, you can hear me. Oh, that's good. Fantastic. To come here. So I think we expect a few more people to join us. So let's give it a bit more time. We have 2 more minutes before the official start of the talk. Okay. How is the audio? Is it okay? Can you hear me just?
Yeah, we can hear you, Jacob.
Wonderful, thank you. Yeah. How's everyone? People are joining. Brilliant. Hello, Russ. Good afternoon. Perfect. Yeah, so this is, I'm slowly going to start laying rules here. So, doing talks remotely can be quite tedious. So I would appreciate if you please interact. There are no bad questions. So if anything's unclear, just raise your hand. Questions.
Sure.
Okay.
So sorry, Professor. I have some problem setting up my camera, and I haven't fixed it, and I have to be like this.
That's okay. That's okay. I just said, if it's, it's nice if it's a bit more interactive. So if people can turn on the cameras, that would be great. I understand sometimes the technical issues and this can't be done, but if it can be done, I'll give you 1 second. Sorry. Okay, cool. So a few more people are joining. I think we have quorum now. So let's slowly get started. Just a reminder for everyone, this talk is supposed to be interactive. So if you have any questions, just speak up. You're welcome to turn on your camera if you can. You're welcome to interrupt at any time. Hey, how are we doing? This will be a lot more interesting for everyone if you ask questions, because to be honest, you know how the world works, right? Most information can now be found on the internet. Everything I talk about is published work. So the real point of this is to make it interactive, for you to ask questions and to engage, because everything you can basically get just by spending time on, YouTube or whatever other video websites. Okay. Cool. I think we have quorum. I think this is good. Arash, what do you think? Should we get started?
Yes. I think we can start. And also, I have to thank you for giving us, making us this link for for the meeting. And I think we could get started. And also, I have to say good morning and thank you for accepting the invitation. It's really an honor. And let's see how it goes. And I'm so excited about it.
Wonderful. Thank you for the very kind invitation, and thank you for joining. And let's go. I will keep admitting people as they come in, obviously. So let's admit everybody here.
Okay. Can I help with admitting the people if that would be a distraction for you, I think.
I think it's okay. You know, I have 2 jobs. I run a big lab. I'm rather used to multitasking, whether I like it or not.
Sure. Thank you.
Okay.
We really appreciate it. Thank you.
Much appreciated. Cool. So let me start by just quickly introducing myself. I'm Jakob Foerster. I run what's called FLAIR, the first lab for research at the University of Oxford. And what FLAIR does is we try to sort of like do everything that is at the frontier, pushing the frontier of what is possible with machine learning. The outline for this talk today that I had in mind is essentially going to talk through the big revolution that's happening in deep reinforcement learning. We will then go on and meet some more people, and then we will talk about what this has enabled. You know, better evaluations, how it's unlocked breakthroughs in curriculum learning, how we've used this to develop new theory, to develop simple algorithms in reinforcement learning, and how we've used this for meta reinforcement learning. And in particular, we've discovered new reinforcement learning algorithms. And then if we have time at the end, I can also talk through some more recent work that's not directly about reinforcement learning, but also quite interesting, the AI scientist. So doing end-to-end science. Yeah, that's roughly what I had in mind. So let's see. And, you know, this is a bit of like, I call this a choose your own adventure, because you're all online. You can let me know what parts are interesting, what parts are boring. I can speed up, I can slow down. Really, because again, making this interactive and giving you a chance to ask questions that you might have for me about the content, about the lab, anything you want really, is a big point of having an online talk rather than watching something online on the internet. So first off, you know, I am sort of, yes, the person who set up FLAIR and run FLAIR, but really all the credit goes to the lab. Here's the lab as of, I think, 6 months ago, right? This is FLAIR. This is the group of people that is behind the vast majority of the work that I'm talking about today, and all the credit goes to my fantastic students. Just to understand, I will assume all of you are quite familiar with reinforcement learning. Is that fair? Can I have a quick thumbs up for everyone who sort of like understands the foundations of reinforcement learning, and, you know, everyone who's like, yep, I got this. Awesome. That's brilliant. So, you know, everyone here, you know, and I heard you had a lecture by Rich Sutton at some point. Is that right? Wow. I mean, winner of the Turing Award. So this is big news. Maybe that means that one day I will also get a Turing Award. You know, if causation and correlation point the right way for us. Okay, cool. So the way that I like to motivate all of this, you know, hyperscale, what this actually means, is to think about 2 different revolutions. And in particular, when I started, like just before I started my PhD, there had been this AlexNet competition. So where AlexNet won on the ImageNet image recognition challenge in 2012. And that was revolutionary because for the first time, a deep learning method really, you know, led to a huge jump in performance on this benchmark that had been around for, you know, decades. And this was in September 2012. And what you can see is the Wikipedia article for AlexNet, right? And you can see this is really like just convolutions, pooling operators. There's nothing magical. But what happened was they figured out, Alex Krzyzewski, how to run these deep neural networks on the GPU. And what this meant is practically that suddenly you no longer needed tens of thousands of CPUs, as Google Brain had been doing up till then, but you can instead run this on a few GPUs. And suddenly we got these large jumps in performance and efficiency. And many people forget this, but deep reinforcement learning, so this is the deep learning revolution 2012, deep reinforcement learning really happened quite closely after, because tabular learning from Sutton and Barter had been around for decades, but finally in 2013, people figured out how to do deep reinforcement learning, i.e. training nonlinear function approximators, for example, being able to process images. Okay, and this happened in 2013. And this is quite astonishing because actually they're only 12 months apart, these two revolutions, deep learning and deep reinforcement learning. But if you look back 12 years later, it turns out that deep RL has been a success, right? Let's assume citation count matters for something. We have something like 30,000 citations for DQN, another 15,000 for another paper here. But we all know what really changed the world forever, and that is deep learning, right? The AlexNet has 160,000 citations, and that's still undercounting the real impact of deep learning, okay? And this begs the question, why is it that deep learning has been so successful while deep reinforcement learning has led to a lot of publications, but hasn't really revolutionized the world, right? I think this is a really important thing to figure out, because what if we could unlock the true potential of deep reinforcement learning, right? Wouldn't that be fantastic? And the hypothesis that my lab has been pursuing is that this is because of the computational inefficiency. So in particular, when we're doing deep reinforcement learning, we have an environment, as you know, because you've all had your reinforcement learning lectures, and this environment is usually implemented on the CPU, okay? In contrast, the agent, the parameters, the learning rules, the updates, all of this runs on the GPU because of the deep neural network. And what this means is you have to orchestrate the CPU and the GPU, and they don't really like talking to each other, right? Imagine you have a trading relationship with a country that doesn't really, you don't get on with. It makes things complicated. Does that make sense? And a lot of the headaches of deep reinforcement learning research and algorithms has been trying to get around this constraint of having the environment on the CPU, having the agent on the GPU, and then having to shuffle data between these two different systems. How has this manifested? It has resulted in a lot of algorithmic complexity. Okay. So for example, I'm showing batched A to C, where we have a number of different actors that are doing data collection on the different CPU threads, and then we're batching it together, and then we're doing backward on the GPUs. And you can see how these different architectures try to get around the fact that you have to both shuffle data efficiently between the CPU and the GPU, while also keeping your GPU ticking along nicely. Okay. And let's just do a little case study. Are there any questions so far, by the way? I do want to remind you that this is supposed to be an interactive talk. I hope you were warned, and that you'll get most out of this by asking questions. So I'm going to just wait here for 10 seconds to give you a chance to ask any questions you might have. Because if any of this is unclear, the rest of the talk will not make much more sense. Any questions? No questions. Can I have a thumbs up for everyone who understands the content? Okay, there's a question, please.
I'm just wondering if in the case of the deep reinforcement learning, the scaling is only the problem, and we don't need any other ideas to get at the core of the intelligence, and our only problem is scaling. Do you think that's the thing, or the scaling law will solve the reinforcement learning, or we have to work on some other things?
It's a key question. So I don't think that scaling is all there is, but I do think that making it easy to scale is a crucial step towards being able to discover better algorithms. Okay. I do think that the sort of difficulty in experimentation has limited our ability of producing good algorithms, because the progress in deep learning is on the back of extremely efficient experimentation and computation. Okay,
Yes,
it's a great
I got
question. One more question here. I see a raised
Can you
hand.
hear me?
Please, yep. Please go ahead.
My question is, in deep learning itself, we have the problem of memory because we have to have I/O to retrieve the image from memory and then move it back. And it is, like the same problem, the same problem that we have in deep learning. And especially for the algorithm like off-policy algorithms that do training. Your example is A to C, which is kind of policy gradient, as I know. And these algorithms need to compute gradient after each episode. But for off-policy ones, we don't have to do so. So it is, in my opinion, exactly like deep learning itself. And my question is, what is the difference between the problem of I/O in image, for example, classification, and the problem that you have stated here?
Yeah, so I think a big difference is you said many things, and these are great points. Thank you. So a big difference is that for the data loading problem, people have actually just figured out really, really smart ways of having pipelines where you can make sure that your GPU does get all the data it needs, and that's a very standardized process where you just need to make sure that you're sort of like shuffling data through the different steps of the pipeline so that something arrives at the GPU at the right time. And crucially, the delay doesn't matter. It doesn't really matter how long it takes me for my data loading process to get data to my GPU, as long as I can make sure there's always data there at any time when I'm ready to do forward backward. In contrast, of course, when you do off-policy reinforcement learning, you have a similar type of issue. But here, there's a lot of dependencies between the staleness of the data and the efficacy of your algorithm, and the exact speed at which you're collecting data in your environment, at which you're playing back. All of this matters suddenly because there are these interaction loops between the agent training on the GPU and the agent collecting data in the environment. And suddenly these things start to matter. So for example, if I quickly go to Hanabi, right, which is one of the card games where we study human-eye coordination, we have actually had a lot of experience in this game. So this is a real-world data point, right? And we had to do a lot of engineering to get to 165 steps per second on an NVIDIA V100, right? And similarly, if we want to run this more in a sort of like a CPU-based system, we were using 100 CPU years to train these algorithms, right? Now, what else could we do? We did a lot of engineering here using C++ to try and be smart about off-policy learning, as you say, that gets around some of these limitations. But even this had really quite complicated architecture, right? Where you have your inference loops, where you're shipping off a model to the inference steps to collect data. You then have, heavily optimized replay buffer that deals with the staleness and the ordering. None of this matters in supervised learning. And then you send trajectories to the training loop, right? And to give you an idea of this, we had problems where if you move from one piece of hardware to another piece of hardware, suddenly the replay ratio, how often you're recycling the same experience, changed and training became unstable. Does that make sense? And none of this matters in supervised learning because as long as you're taking an IID batch of data and you make sure your GPU stays busy, these questions don't appear. I saw one more hands up.
I see. Thank you.
It was a great question. Thank you.
Hi, Professor. Can you hear me?
Yes, of course.
Yeah. My question was that don't you think that generalization is a much more pressing issue here? Because, deep learning algorithms have been known for their generalization, that they can perform really well on unseen data. But for reinforcement learning, what I witnessed from my own experience is that these agents become attached somehow to their environment. Any tiny change in the environment can, mess everything up. And the policy that could work on one environment it cannot be generalized into other environments.
So
Something that
great
yeah.
question. Thank you. So just quickly on this, it's a bit ironic when you say deep learning is great, but reinforcement learning, it doesn't have those properties. Because let's remember the backbone of all the policies in the deep neural networks, right? So obviously, to the extent that deep learning generalizes, if it did, we'd expect the same to be true for the policies we're training here. Right? Just to be very, very clear, because ultimately we are using deep neural networks as the backbone for the experimentation. Now, having said this, a key part of the talk will be about generalization and robustness, right? And just to be also very clear, I don't think we have good evidence that deep learning truly generalizes. Yes, it generalizes in distribution, but no, we don't have any proofs or guarantees that deep learning generalizes out of distribution. So we have to be a little bit careful when we claim things like deep learning generalizes. Okay. We have a couple more people joining the talk. Welcome, everyone. As a reminder, this is an interactive talk. We got a lot of great questions. Okay, let me move on to the next slide. So basically what one takeaway here is deep reinforcement learning had lost the hardware lottery, right? Deep learning was a great fit for the GPU, but deep reinforcement learning is not a great fit for the GPU. And one path forward here to at least make it easier to study deep RL quickly and efficiently is to bring the GPU now to deep reinforcement learning in a way that's a lot more natural than having that CPU-GPU mess. And it's a very simple idea. We're simply going to run the environment along with our agent on the same GPU. Okay? And you now might think you have to write custom CUDA kernels or go very, very low level. But the good news is recently a framework came out. It's called Jax. Can I have a show of hands, please? Thumbs up if you've used Jax and if you're familiar with it. Nobody. One person. Okay. Hello, Mia. Cool. Okay, cool. Quite a few of you. So this has really been the key unlock for all the research that I will talk about in this talk, right? And basically what Jax allows you to do is it allows you to efficiently interact with the GPU at a level of flexibility that makes it possible to not just specify deep neural networks, but also code up environments to run on the GPU. It offers just-in-time compilation, auto-vectorization, you can do automatic differentiation, and crucially, you can parallelize. So what this means is if you implement the environment in Jax once, you can now go and you can vmap it. So if I have one instance of the environment implemented, I can use the function Jax vmap and add a batch dimension to this, which means I can now run a large number of environments in parallel. Okay. And obviously, like some of this, you could have done with PyTorch. In fact, the first time we did end-to-end running on the GPU was my student Chris Liu, when he implemented learning environment style in PyTorch. But it's not made for this purpose. It is a deep learning framework, and therefore it required quite a lot of sort of intellectual gymnastics to make things work. And Jax greatly simplified this. Okay, we've released all of this as a library, pure Jax-RL. It's been quite popular on GitHub. And what this allows you is you can vectorize entire deep reinforcement training loops and run all of this jointly on the GPU. Okay, let's look at what this means in practice. So here, the red bar is the time it takes to train a single RL agent in a previous environment, in a previous implementation. And then you can see how many agents we can train in the same time on an NVIDIA A100 GPU, NVIDIA A40. Now, you might think those are kind of, state-of-the-art expensive GPUs at blah, blah, blah. However, for example, on 4090s, we also get really, really good speedups. Okay, so you don't have to go to the, state-of-the-art deep learning GPU. Something that's much close to a gaming GPU will also give you great performance. Okay, So one concern you should all have, there should be a question right now, which is, but isn't this quite limiting? Because you can only run this for environments that have been implemented in Jax. Most environments have not been implemented in Jax, can run on the GPU. So we aim to address this by providing new implementations of more diverse environments in Jax. And the first paper along these lines is Kinetics, which is pushing for end-to-end foundation models. Let's go back to the question of generalization. How do we get towards generalist agents and foundation models for decision-making? And I should point out, this is an oral at the International Conference of Learning Representations in 2025. So what the goal here is what it says on the can. We're trying to train an agent that can generalize from this random distribution of environments. Think of this as the internet of environments, low quality, but very, very large amounts of data where the agent can try out and can learn and can train to achieve its goals. And then we're testing if this agent is capable of generalizing to a small number of held out test environments. Okay, so the goal is to address exactly the question of generalization, right? The comment was made earlier by one of your colleagues that deep RL is so brittle that if you change anything about the environment, everything fails. And precisely, we're now going to ask, can we train on this one distribution that's extraordinarily broad and general to then have agents that generalize to these held out, handcrafted test environments? Now, to make it a meaningful transfer, obviously the task needs to be well specified. So each task on the left-hand side is specified by having an agent that needs to make sure that the green shape touches the blue shape. So there's a green circle here and there, while avoiding to touch the red. Okay. Now, what does a task mean? We need to have a controller, so you need to be able to interact. And what this means here is we can add engines, we can add joins and rocket engines that the agent can control. Are there any questions about the basic setup of Kinetics? Okay, then let me proceed, and I will give a brief sort of interlude on curriculum learning. And in particular, there's a prominent field now that's called unsupervised environment design, where the goal is to develop curricula that allow agents to generalize better. Okay. And my lab has published quite a lot in this field. And just for sort of completeness, this unsupervised environment design, UED, has been around for a few years now, and there's a couple of hundred papers basically in this field. And what these papers have done historically is that they focused on these grid worlds, on these relatively simple grid world tasks, and a few other environments. And the goal of UED is to train this agent on that distribution, on this very undescriptive broad distribution, and making sure that it can generalize to the tails of the distribution, so that you're good everywhere. So what my lab did recently is we asked, what if we go from the standard environments in UED towards a setting that is a lot closer to the real world, like this multi-robot navigation system on the right-hand side. Now, studying this system itself is obviously out of scope because we have to simulate 3D physics and. But we designed a 2D environment that has continuous actions, there's little robots moving around, they have LiDAR readings. And again, we have a parameterized distribution, which means we can generate an arbitrary number of these environments. But we don't know the real environment at test times, so we want to generalize to the tails of the distribution. And what we did in this paper, we basically benchmarked in this environment that's a little bit close to the real world, but still quite close to what people had studied. We benchmarked all the existing methods in the field of UED that were previously successful and had beaten simply training on the random distribution over these environments. And what we found is that none of the existing methods were able to beat just drawing random samples and training on those. When we found this, we asked what would be a meaningful, simple method that we expect to actually work. And this we called SFL, or sampling for learnability. What we mean by this is learnability being the difference between always succeeding and the current performance of the agents. So 1 is the probability of success of 1. Current performance of the agents, that tells you how much gap upwards there is, weighted by the probability of getting a learning signal. So it's P times 1 minus P. Okay. And it turns out that if you simply create a curriculum based on this scoring function of learnability, you get an agent that generalizes much better to the tails of the distribution. So 100% means we're drawing randomly from all of the levels. 10% means we're ranking the levels by solve rate by the agent, and then evaluating the performance of the agent on the 10% of the tail. And then 1% respectively means what's the success rate of the agent on 1% of the hardest levels for that agent. And what you see is that our curriculum is the only one that helps the agent perform better at the tails of the distribution. Are there any questions on this? Can I have a show of hands? Who in the audience had heard of UED or unsupervised environment design before? Is that something you're all familiar with? Thumbs up if you've come across UED before. Nobody. Okay, then I should probably include a little bit more background slides. Okay, there are a few people here. So in a nutshell, UED tries to get to the core of how we can train generalizable agents. Amir, I see a question from you.
I have seen some work from Jeff Kulun. Maybe it is related to their work. They were training open-ended environments using reinforcement. I wonder if there is any connection between this work and.
Yeah, so often the two fields of unsupervised environment design, open-endedness are treated similarly because they share the idea of generating new problems and training agents that can solve those problems, and always pushing the frontier of learnability. Okay. The big difference is that in unsupervised environment design, there is an ultimate goal we're trying to achieve, which is robustness of the agent on holdout tails of the distribution. In open-endedness, there's often a lot more vague because it's open-ended, right? So you can think of of UED as being a more sort of narrowly defined subset of open-endedness. Okay, I see there was a comment here in the chat. Let's take a quick look. Is it possible to explore alternatives to? Yeah, wonderful. Continual architectures for hyper tuning. We'll get into this a lot. I mean, a lot of this talk will be about meta learning once we get. Okay, so fast forward. This work was published at, I think, Europe's last year. And we came up with this very, very simple curriculum heuristic, which is look at the difference between solve rate of the agent and perfect solve rate, and weigh this by the probability of seeing a reward signal in binary settings. But crucially, we could only get to this simple equation because we had an efficient implementation, Jax navigation, Jax implementations of all these baseline algorithms. So we could fairly tune the algorithms. And we could go and experiment, run large numbers of experiments, trying to compare these algorithms fairly in a new environment. Okay, and this is crucial because previous implementations would have been 100 or 1,000 times slower, roughly. And you can imagine at that point it becomes prohibitive to do fair evaluation of these different algorithms. So that gets to the first question. Do we think that scale is all there is to making reinforcement learning work? Well, no. But by having scale, by being able to do experimentation faster and more reliable and better, we can then discover the algorithmic breakthroughs that will allow us to build RL algorithms that actually work. And often, it's a lot harder to come to a simple, effective algorithm than it is to cobble together something that's vastly complicated, is not fairly benchmarked, and works in your limited explorations. So this is crucial to understand. I'm not claiming that scale is all there is, but I am claiming that efficient experimentation and scale will facilitate us to make progress better and more reliable as scientists in reinforcement learning. So let's look at this example. We came up with this algorithm through loads of thorough experimentation in Jax-accelerated GPU hyperscale environments. But what happened next is when we take that same algorithm, P times 1 minus P, SFL, and we deploy it on kinetics on this very, very different task, it's the only one that gives us an uplift in generalization of allowing our agent to generalize from this random set of training environments that I showed you to these hard holdout test environments, right? And this is a little bit mind-boggling because this distribution looks so different from the actual task that we implemented in kinetics. And I should say, by the way, if you're interested in this, kinetics, we have an online platform. We can design new environments, new holdout environments. You can test our agent in those environments, and you can be the agent. You can go in and you can play with these. You can actually control the robot yourself. And obviously, you know, Grasper, Half-Cheetah, Acrobot, for those of you who know reinforcement learning, these are all different environments. We can parameterize them all within that same 2D physics platform. And indeed, kinetics, we get a zero-shot performance improvement by running SFL, the ranking algorithm, on that distribution of randomized environments. And that's shown here with the blue line that goes up. Right? And this is both for the small levels, the medium levels, and to some extent for the large levels. Now you might ask, why do we not succeed zero shot at the hardest tasks? And that's because there's an open problem here scientifically, which is learning stagnation. It turns out our agent continuously has levels that are at the front of learnability, but it simply doesn't manage to generalize, right? And this is not on the deep RL algorithm, because remember, we're using the same deep learning networks as others, right? So it's an open problem. It doesn't take much to get there to reproduce it. And I encourage all of you to work on this, because it turns out deep reinforcement learning, even in simulation, gets to a point where learning stagnates, even after doing thorough hyperparameter sweeps and after trying to do all we can to make this agent generalize better. And this can be tested, this can be reproduced by all of you with relatively limited compute resources. You don't need state-of-the-art clusters for this. I don't know what your current access to these machines is, because obviously academia differs vastly in that dimension. So this was a really cool result, because obviously, we designed this for one. We had come up with this algorithm in one environment at a generalized zero shot to another environment that looks very different. Then my student Thomas Foerster said, well, you know what? If this works so well on that different RL problem, why don't we just deploy it on another very, very different task? And that is using reinforcement learning to train LLMs to reason better. And that's our recent submission. It's on the archive, Learning to Reason at the Frontier of Learnability. And here what Tom found was, indeed, if you just deploy that same SFL algorithm on top of existing state-of-the-art methods like Vine PPO, these LLMs are now generalizing much better in terms of test time accuracy. And it's not just that the agents train faster, you get higher performance at convergence. And this was one of the first times that I'd seen an algorithm that was developed in deep RL generalized to the LLM setting, which commonly use very, very different methods. We know that GRPO looks quite different from PPO, for example. But here at the curriculum level, there was a direct transfer of methods from those developed for deep RL from tabula rasa to those that use deep RL on top of LLMs. Are there any questions on this? Wow, cool. There's a comment. I see people like it. Oh, that's awesome. Thank you, Ali. Okay, anything else here? Any questions? If not, I will move on, because life is short and time is of the essence. Cool. So obviously, having a foundation model, one of the things we care about is zero-shot generalization. But the other question that foundation models allow us is efficient fine-tuning. Okay, so this is something else that we looked at. And basically what we did is we took these hard test cases and we asked, what if I train a tabula rasa PPO agent only on that one specific environment? That's the blue line. Or if I take my generalist agent and I fine-tune it on that one specific target environment. And what you can see here is there were some examples where fine-tuning vastly outperformed, both in terms of sample efficiency and final learning performance, training from scratch, right? There were also a couple of examples where, or like at least one example here, where the lines were, more intertwined or upside down. But there's evidence here. Coming back to that first question, can deep RL ever generalize? That we've gone a long step towards a foundation model for deep reinforcement learning, because it's generalized zero shot to unseen harder settings. And if you fine tune it, you get much better performance on the target domains, which were the two key components for unlocking the success of foundation models in non-agentic settings. We were done, so we also shipped a lot more environments to make it easy to study multi-agent learning, because multi-agent interactions are the future. So let's try and make it easy for everyone to work on these environments quickly and efficiently. So we have this suite called Jax-Smart. Jax-Smart supports 8 different environment classes across fully cooperative learning, zero-shot coordination, general sum learning, and it's blazingly efficient. It's all online and open sourced, and you're welcome to play with it. And we get these vast speed ups of up to 10 to the 4, roughly, compared to the previous implementations. Now you can imagine it makes a difference if your algorithm finishes in an hour or in 10,000 hours, right? The experimentation loop here looks quite different from what was possible before. What we also did as part of this is we went and we took the popular environment SMAC, Stack of Multi-Agent Challenge, that comes out of my PhD work, where we train different agents to compete in the game of StarCraft in the problem of microcontrol. And we re-implemented this as a symbolic environment in Jax, where you can ask exactly the same research questions, but this runs symbolic all on the GPU, while this would have required vast amounts of RAM and CPU support. So very quickly, Jax-Smart basically combines very, very high speed. So we can now achieve 20,000 steps per second on Hanabi. Remember, we started out this talk with 150 steps per second on Hanabi. Ease of use because we're Python-based, and we support a lot of different environments. If you're interested, there's a blog post on this. Again, everything I'm talking about is open sourced. Everything is open science. We're trying to make AI accessible to humanity. We've also gone and we've implemented a Jax-accelerated version of the order book simulator, because I care about multi-agent settings. I care about strategic multi-agent settings, and finance is a great example. This was published at iCarve and at Conference on AI for Finance, and won the Best Academic Paper Award. For those of you who don't know, basically, the financial markets, at the core, it's an order book. It's a clearing mechanism to determine a price, given that there's a large number of different players who can submit orders anytime. And you're basically tracking what people are willing to pay for a given stock and what people are asking for as a minimum, right? So for example, here's somebody saying, I'm offering, $255 for Tesla stock. And here's somebody saying, I will need at least $257 for Tesla stock. Obviously, there's no trade because there is a spread between the bid and the ask. However, if that crosses, then there's a trade because somebody offers more money than somebody else needs to get rid of their stuff, right? It's a very, very simple idea, but it can lead to very, very rich interactions, such as, for example, the flash crash in 2010, where the DAX crashed quickly by a large amount, flash crash, because of algorithmic trading. And crucially, we have agents interacting with humans in all of this. So we, again, want to accelerate study. This hasn't really been studied at scale in the academic community. We want to change this because I frankly think it's quite a shame that so many smart people go work in finance. And I figured if we just solve finance using machine learning, we'll get all that brain capacity to work on more interesting problems. So let's just solve finance. And to do this, what we tried is we implemented this clearing book, the order book mechanisms in Jax. We get 75x speed up. And we also did quite interesting work based on this to build generative models for the financial data flow, right? So this is our end-to-end order book modeling project that we've also published recently. It's all open source, again, obviously. And what we did is we trained S5 simplified state space model to predict the order flow. This all sounds quite abstract, but you can think of it as simple as you're all familiar with LLMs. How do LLMs work? Well, I have a tokenized stream of data. I map from text into a set of tokens, and then I predict the next token given the history of previous tokens. And I can do this with any type of data. And in particular, I can do it with financial data, with the flow of orders. So for example, if I call up the exchange and say, hey, please, I'd like to sell Tesla stock at $255, then what the exchange will do is they'll add that order message to the order book, and the order message consists of different fields, which is the type. Do I want to sell? Do I want to buy? Do I want to modify? The price, the size, timing information when this order is coming in. And then also, if I'm modifying an order, I repeat the information about the order that's being modified. And what we did is we tokenized all of this losslessly. So we have an exact representation of this order flow in tokens. And then we trained a model that takes in these sequences of messages and predicts the next token. And crucially, because we implemented our simulator on the GPU, we can now also take the message flow that's being produced, check it for correctness, and then calculate an updated state of the order book, which is the state that tracks all the existing orders on the exchange. Okay. And we also shipped the benchmark that evaluates all of this. And basically, what we found is that our current models that we have are a lot better in producing more realistic flow data than anything ever published before. So that's good because it means we can now study reinforcement learning in more realistic problem settings, including the financial market, and we can do so efficiently because we have GPU acceleration. Are there any questions? Or is everyone just too sort of, yeah? Arash.
I have a question. I have a question about Jax-MAR. I wondered how correct the symbolic representation of that complex environment is when we simulate it, and can we extend that that complex simulation on the GPU and do more correct simulation?
I mean, sky's the limit, right? If you have the time, you can go in and you can make this representation more accurate, right? That's up to you. If you want to modify it, it's open source, right? But to be clear, I'm not suggesting that we train policies here and then deploy policies on the left-hand side. Not supposed to be a perfect proxy. What I'm suggesting is we use the right-hand side to study algorithms and develop new methods. Because here we can get 10 to the 4 more samples, and we can develop these algorithms faster. And then these algorithms should be able to generalize to training policies sample efficiently in the real world. Okay, so this is crucial. You don't have to build perfect proxies of the real world for the development and the study of algorithms. And I will give you examples of this. Because what we've also done is we've gone in and we've done a lot of meta learning in Jax-MAR and in Jax and on the GPU. I want to highlight another paper quickly. So this is a new environment that we pushed for open-ended learning. Jakob N came up earlier, a great friend of mine. Please say hello to him if you invite him to give a talk. And here we said, how can we just make RL environments richer, more open-ended, more diverse? And what we did is we took inspiration from the craft environment and we just made it a lot more complex by adding all these different new tokens, different levels. Agents can explore, agents can go to different types of layouts. And if you go to our blog post, you can actually see us trying to play the game a little bit, and you will find that I'm terrible at it. Okay. So what's interesting here is it's not just blazing fast. You can see the speed up as we scale up the number of environments in parallel. But it's also really hard because our best algorithms at the time get around 16% of the max reward in this environment after 1 billion time steps. And you can get to 1 billion time steps pretty quickly in 24 hours. Okay. I now want to talk about some of the specific advancements we've made using our accelerated RL environments to develop better, simple algorithms again. Again, I think there's nothing harder than to develop simple algorithms. Right? It's very easy to cobble together something complicated and claim it works, but most likely this will not generalize to any new problem setting. So what we did here is, excuse me, we analyzed temporal difference learning from a theoretical point of view. The slides by my postdoc, Matty Fellows. And there's all this work on, why is it unstable because not a proper gradient? How can we analyze it? Well, we used Jacobian, and then we stabilized it, making minimal interventions by having layer norm and L2 regularization. There's a lot of theory in the paper that I would like to point you to, but basically what this says is batch norm makes the policy myopic. So your Q function becomes your reward, which is bad because we have to be long-sighted to make good decisions. But Matty derived fantastic theorem which shows that if you have layer norm plus L2 regularization, you can actually make off-policy learning stable. We validated this in a tabular setting, but we also then simplified the algorithm to the bare bones. Okay? So if you remember Rich Satton's Q learning, right, it was this very simple idea. The agent interacts with the environment, gets a transition, and learns on that transition. Tabular Q learning, right? My target is R plus gamma Q star, right? And I minimize the difference to make my current Q value and my target value, right? Then already DQN had to go and add replay buffers, add target networks, do a bunch of stuff to just make Q learning work in the context of deep neural networks with functional approximation. And then we went on to having distributed DQN, where we have, again, all these complicated environment rollouts. We copy the weights around. We have staleness, yada-da-da-da-da. But then in our simplified Q learning, DQN, and part of Q learning Q networks, what we did is we get rid of all this complexity, and we simply use the fact that we can parallelize across the GPU to take a number of parallelized rollouts, and we do online learning on each of the transitions in batch on the same GPU. And there's no more target networks, no replay, just temporal difference learning as Satton and Bato had originally imagined it. So this is the pseudocode for PQN. And it's mind-bogglingly simple. We just unroll episodes in parallel across the different batch entries on the GPU using on-GPU vectorization in Jax. And you'll recognize this is just a target. We just calculate the target without a target network by looking at the reward plus gamma times the Q star, the arcmax over the actions in the next state. Okay? It is as simple as this, and then we're doing online learning by regressing our current Q value against that target. And what's nice about this is, in DQN, because you're unrolling a single environment thread, you then get these correlated updates from that same trajectory that you're throwing into the buffer. Instead, in PQN, we're unrolling a large number of parallel trajectories, and then our learning step samples across that same time slice, which means we're getting a much more ergodic, a better approximation of the ergodic distribution in our learning update. Again, this is a mind-bogglingly simple algorithm, and what it has allowed us to build a competitive version to PPO when running on the GPU. So in all our sweeps, this version, this extraordinarily simplified version, is competitive to PPO and DQN while being orders of magnitude more efficient than DQN and much simpler than PPO. And we hope that this will unlock new theory and a new renaissance of simple and scalable and sound algorithms. Now, we can't just use theory to design new algorithms ourselves. We can also use theory and GPU acceleration to discover new algorithms using meta-reinforcement learning. We published a paper on mirror learning in 2022 with some of our fantastic collaborators. Kuba was a master's student here at Flare, and Krishna was a postdoc at the time. And what mirror learning says is, I can describe a large class of different reinforcement learning algorithms that are new state of the art, as optimizing an objective function that tries to maximize the expected Q value of my data collection policy under my new policy, while minimizing a drift function, a penalty function that says how different is my new policy from my old policy. And as long as this drift function obeys 4 simple requirements, I will obtain monotonic improvement properties, which means every policy update will give me a high expected return than the previous one. And what's nice about this simple theoretical framework and the proofs is that it describes all of these different RL algorithms and gives all of these RL algorithms now convergence guarantees. And in particular, PPO, you've probably wondered, like, why does PPO work, right? It's inspired by TRPO, but the connections are so loose. It's very odd to think about the fact, why should this thing converge? Why should it be good? Mirror learning says, forget about all these connections to TRPO. What PPO is, it's a specific instantiation of a mirror learning algorithm where this drift function includes the clip, yada, 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 and all of this. So you can write PPO in these terms. But this begs a natural question because, we have this point support of things that people have tried. Some of them are really good. But there's an entire universe out there. Because we just have to oblige the mirror learning criteria for the drift function, and then we'll be fine. So why don't we go and just explore this space algorithmically? And that's what we did with our 2022 paper at NeurIPS, DPO, Discover Policy Optimization, where we meta-learned a drift operator. Okay? So here, so far, these things were hand designed for humans, which are really knowing what they were doing. Let's just say we parameterize this as a neural network. So now we parameterize this drift operator that gives you a penalty between the previous policy and the current policy. And in particular, we're going to learn this by doing evolution strategies to estimate the gradient, the meta gradient. Show of hands, who here has heard of evolution strategies or ES from OpenAI? Cool. Awesome. Quite a few of them. It's brilliant. In a nutshell, what ES does is it says if I have a process that depends on some parameters phi, I have a fitness function, say the expected return of my policy is trained under that drift operator parameters per phi. And I want to estimate the gradient. How does phi change the final fitness? Then, of course, I could try and differentiate through this learning loop if I have white box access to it. But then I have to unload 10,000 learning steps. You can imagine that meta gradient looks quite gnarly. Instead, it is sufficient to simply take random explorations from a Gaussian around the current mean value of phi. And I can estimate the meta gradient by just taking a weighted average of the fitness under my perturbation epsilon, weighted by that epsilon. So I'm exploring from a Gaussian. I'm drawing epsilon from a Gaussian around my current value is phi. And then I'm just doing a weighted average where it weight the directionality of my epsilon, counting it with the weight of the fitness induced by phi, by epsilon. And that's an unbiased estimate of my meta gradient, which is kind of mind-blowing, but you can derive it in like two lines of algebra. So this has become the meta gradient estimate of choice in my lab because it works extremely well for large polarization, and it's been a lot more stable than 200 papers written on meta gradients, some of them by myself in reinforcement learning. And what we did is we learned this drift function phi. We meta-learned it on the ant environment, and what we found is this drift function actually generalized to a number of foul-dot environments, quite well zero-shot. So this again gets to the question: what should I expect to generalize? Not my policies, unless I have good coverage and it's in distribution, in support, blah blah blah. What I should expect to generalize are my algorithms. In particular, I can meta-learn algorithms, I can discover algorithms in my environment, and I can now train them and deploy them in other environments. How are we doing on time? Can I have a quick check-in? How much more time do we have? Because I think this was scheduled for about an hour.
We have. I think we talked about 90 minutes, but we are, if you can give us more time, we are.
Okay, so we have about 9, so we can talk a bit. Okay, fine. So we're not running out of time here, yeah? That's what I want to check.
No. That's on your side. How much it can be, we are happy to listen.
Okay, fantastic.
Thank you.
Very kind. So then I'll slow down a little bit here because I think we've actually gone through a lot of material, but it's good. Are there any questions so far? I went quite fast in the last, like 10 slides. Anything here that is around ES, meta learning, what we're actually doing, right? Just to be very, very clear, right? We're trying to estimate the optimal parameters for this drift function, but the drift function is part of the RL training loop. So to evaluate a parameter phi, say phi naught, I have to actually train the entire RL agent for that phi, right? And this training loop takes, maybe 10,000 grain updates, maybe 1 million environment interactions, for example. And then I get a fitness for this. I do this n times in parallel, and then I estimate my meta gradient, I update my mean value phi, right? And then I iterate. Okay? That's how this goes. And in principle, this is something where before Jax, groups across the large industry labs would have taken entire GPU and CPU clusters to do this. And now you can run this on a couple of. Okay, let's try to understand because it's quite mysterious. Yep, Ali?
I have a question. I think the traditional ways to bound your probabilities to be on policy and do not get away from your policy is something like KL or these things. But how do you make sure that with your new approach that you generalize this getting away as a D can provide bounding on your policy?
Right, so what the mirror learning paper says, in principle, theoretically, right? The D doesn't need to be very sophisticated, right? As long as your D obliges a property that it's 0 for 0, so that the penalty is 0 when the old policy is the new policy, and you have 0 gradient, and it's monotonic, then you will obtain these convergence properties as time goes to infinity. Okay. So this entire space of mirror functions, which includes, K-regularization, PPO-like clips, and so on, in principle has convergence properties. Now, obviously, in practice, it matters which D you choose, because you have to trade off between, being optimistic and being conservative. You have to trade off exploration and exploitation. And that's what we're trying to do here. We're trying to learn these Ds so that they allow us to learn fast and efficiently. Now, there are no guarantees, right, beyond the fact that all of these Ds will in principle give you at some point optimal convergence, that if you meta train on one environment, you will generalize to others. You can't guarantee this unless you train on many, many environments. But empirically, this is what we found. Okay, so here we meta trained only on one environment, and we get that red line here, learn policy optimization, and that red line was extremely competitive in very different environments, including humanoid and half cheetah. That's empirical finding. Okay, let's understand what we actually learned here. So this plot is a little bit mind-boggling, but I hear you all go to a fantastic university, some of the sharpest people in your country. So let's do it. Okay, but if it is unclear, do let me know. So what we're plotting here is the policy ratio on the x-axis, which is the ratio between the likelihood of a given action in a given state and the new policy versus the old policy. Okay, and we're parameterizing as e to the power of something, just for visualization purposes. So e to the power of naught means the ratio is 1, which means the likelihood of that action is the same under the old and the new policy. E to the 0.5 means it's slightly above 1, which means we're now taking the action more likely under the new policy compared to the old policy. The old policy being the data collection policy. So again, I have a current policy. I send this out into the world to collect data. And now I have the batch of data, and I'm deciding how should I update my new policy, my next iterate, to maximize my expected return. Okay. So this means on the x-axis to the right-hand side that I'm making actions more likely compared to the collection policy. But on the left-hand side, either minus 0.5 means I've made the actions less likely. That's the x-axis. On the y-axis, I'm putting the advantage, which is the advantage from RL, the same thing that, Sutton and Barker talk about in the book, the difference between what happened in my rollout compared to my expectations. So it's Q minus V. Okay. Positive advantage means something good happened, better than expected. Negative advantage means something bad happened, worse than expected. And the coloring here is the derivative of the PPO objective. Okay. Red means positive, blue means negative, and gray means 0. Can anyone tell me what the gray areas in this plot are? I'll give all of you, say, 30 seconds to think through this and collect your courage. And then please raise your hand. There are no bad answers. Okay. What are the gray areas in the plot? Yep. Nazir?
Hello?
Hey.
Can you hear me?
Of course.
Yeah, great. Thanks. So from the looks of it, I think that gray area, okay, means that the norm of the derivative is 0. And when we are emphasizing on an action and we are getting more positive advantage over the previous policy, so we want to keep it that way. So we do not want to change the policy in any direction.
Why is this? This is true, but why is this? Remember, this is PPO. What part of the PPO algorithm are we looking at here?
Okay, I don't understand the objective clearly here. I don't know. So,
Well, so
PPO.
Yeah. What does PPO have? What does PPO do algorithmically?
It clips the. Okay, it
clips.
tries to keep. Yeah.
It clips. What you're looking at here is the PPO clip. Okay.
Yeah.
That's what we're looking at exactly, right? So if we have a policy, we haven't yet moved away from our original policy, so the ratio is equal to 1, right? And we have a positive advantage. We're up here. What happens? We're going to make those actions more likely. The gradient is positive. Okay. And we're going to make those actions more likely, more likely, more likely. The policy ratio increases, and then we stop. So we've hit the PPO clip, and the PPO clip tries to prevent us from moving too far away from the correction policy. And likewise, on the negative side, if we have a negative advantage and we have the correction policy, we're going to make those actions less likely, and we're going to move until we hit the clip and we stop. Okay.
Yeah.
So this is what PPO does, right? PPO as an objective, you can now look at it and you get it, right? That's the derivative of the PPO objective as a function of those two parameters, the advantage and the policy ratio. That's all the clip term depends upon, and the gradient update. So what we're going to do is we're going to push, and we're going to stop pushing when we reach the clip ratio, right? On the positive and negative advantages. Now let's look at what our meta-learning algorithm resulted in, right? So here's PPO, and here's the learned policy objective on the right-hand side. And a few things jump out immediately. First off, they share quite a lot of structure, but they also differ, right? So you have these red regions, blue regions here, but other things are happening. And let's look at this. So in particular, can anyone tell me what this red region, so let's actually go back here, right? We have a red region at the bottom left, while we have a gray region in PPO. What does this red region do? Compared to having a gray region there, like we have in PPO. Yeah? Ali Reza?
I think when we have a low advantage and our policy and likelihood of the action that gives this low advantage is below some threshold, it encourages that
It encourages. What does that mean? What happens? Say I'm sitting here right now. Where am I being pushed?
toward doing that action, which gives you lower advantage.
Right. So this is quite odd, right? Because I have a negative advantage. I have an action which is bad. Something bad happened, right? And the algorithm says positive derivative, which makes the action more likely, which pushes me along here, along the x-axis to the right. And interestingly, this was developed independently by humans. They discovered this called rollback, right? Because PPO says, if you go along this axis and you hit that ratio, we will stop giving you gradients. But it also means if you ever overshoot and you find yourself in this area, you just stay here. We won't get you back to the clip. Instead, what LPO had discovered was to actually push you back towards the clip. You've overshot, right? You've made an action too unlikely compared to the collection policy. So let's bring it back. The other feature that stands out is cautious optimism for positive advantages, right? So PPO just stops it, has this line that goes down. But our algorithm says, well, it's okay to update and move away from the collection policy unless things look too good to be true. You're only allowed to do this for small advantages, interestingly, right? As long as the advantage is small, it's okay, keep going, right? And what this basically says, if somebody, you try something out for the first time and somebody says, you just made $1 billion. You probably don't just want to go and do this all the time. It sounds a bit too good to be true. However, they say, well, you just made like $5 extra. It's like, well, you know what? That sounds reasonable. That doesn't sound like a fluke. Let me try to do this more often. Okay. And what we also found is implicitly this algorithm does push towards more randomness by pushing a little bit towards uniform distribution. And then we also have all these secondary features, which basically we don't understand. There's stuff that happens around 0, and we don't know what they do. So this is great. This is a neural network that we trained. There's obviously value in having algorithms you can just write down as a few lines of, Jax code. So what we also did is we tried to parameterize this algorithmically. Oh, the rollback is counterintuitive. Why is rollback good? Why is this good? Well, because remember, PPO says you want to stay close to your collection policy, right? PPO, the whole point of the clip is you don't want to leave a bound of confidence around your current policy. You want to stay within a certain amount of density from your current policy. But learning is stochastic and you can overshoot, right? And it's a nonlinear learning problem in your function approximators, which means you can find yourself too far away from your collection policy. And rollback pushes you back towards your collection policy until you hit the clip. Does that make sense?
I mean, you're trying to encourage that action, right? The action which has a bad advantage.
Yeah.
So why should we try to encourage something that gives us less advantage?
Because you're outside your zone of confidence, right? Fundamentally, when you design the PPO objective, the clip says we only trust policies intuitively. We trust data within a certain probability ball around our collection policy. Okay. And we shouldn't update our policy too far away from that zone of confidence. We should make sure that if we collect it from a policy A and we're deploying A prime next, that A prime is similar to A. Because all the data we've seen so far, all the data was collected by A. So we're now deploying A prime, and A prime is vastly different. Anything can happen, and it can become unstable. Okay. And here, what happened is if we find ourselves in this quadrant, we've made A prime very dissimilar to A. We've made actions a lot less likely than they were under A. And what Rollback says is, bring your policy A prime back to A. Go back to area of confidence, even if this means paying a price in advantages. Okay.
Right. Thank you.
Great question. Thank you. So we've done all of this, but then we went and said, let's actually parameterize, like, as a closed form solution, an algorithm here. And we call this DPO, discovered price optimization. And this was done by my student, Alistair Letcher, math background. I mean, actually maths, I should call out quickly. If you can strengthen your math skills, strong mathematical intuitions are one of the most useful things in life, because it will allow you a deep understanding of the planet and the world in a very confusing reality. Physics, maths, statistics, the foundations, right, of allowing you to make sense of a very noisy and complicated world. And it turns out this DPO, worked well in the environment and where we specified it, but then it also generalized quite well again to other environments, sometimes beating PPO, actually quite often beating PPO, crucially using the hyperparameters that were tuned for PPO. So we didn't retune any hyperparameters here. And then we also tried this in very, very different environments. So for example, the mini test suite in Jax, right, which are symbolic implementations of Atari games. Okay, so this was a nice loop of first discovering algorithms using Jax, using evolution strategies in neural networks, and then distilling these by analyzing them into closed form solutions. Okay, but there's another strength of doing meta learning rather than designing algorithms by hand, and that is that in principle we can consider much richer classes of algorithms. Right. So PPO was this thing that was tuned by John Schulman over years to come up with like a really well-tuned algorithm. But obviously, you can't tune that algorithm for example, different circumstances, different environments, because it's very difficult to design one of these algorithms for a different stage of training, for example. But that's exactly what we can do with meta learning. So what we said is, what if we just take the same learning loop, learn price optimization, and we just make it time conscious. We just allow the agent to condition on how far through training it has progressed, and we now meta learn one drift function per point in training. And what you can see here is that the agent learns to condition that drift function on the training progress. And in particular, it does so by moving from a more exploratory, optimistic version to a more conservative version of the drift function over the course of meta test, which is the RL training loop. Okay, this was published at ICLR. I encourage you to take a look to see the full results. And this gives you an idea of sort of what is possible suddenly, right? Because we have these algorithms that can be trained efficiently on the GPU, you can make algorithmic changes that are quite small, but change the outcome of what is being discovered by the agent drastically. And this generalized much better, this worked much better, not just within meta train distribution, but also across. And what we found is that now, if we look at Minitab, we get we beat PPO by a large margin across all measures of robustness, including the median, interquartile mean performance, and the optimality gap. Okay. This just gives you an idea of what is possible now that we have this efficient learning loop. And again, I don't think we should be implementing the reality in Jax. We should be using this fast experimentation loop to develop better algorithms or meta-learn better algorithms that we can then implement in slow Python-based environments or in the real world to have robust and sample efficient learning. I just gave you a quick run through of what my lab has done in the last couple of years. This slide is now outdated. I recommend follow me on any platform, look at our website, but we've obviously done a lot more work in this space. We have tens of top conference publications every year. As I said, we have an oral coming up, we have another spotlight. We are one of the leading reinforcement learning, and by now also LLM labs, pushing the frontier of what is possible in machine learning. So that's that. Let me conclude this part of the talk. So we're in the middle of a revolution. Obviously, like RL is now working, and many speedups of orders of magnitude speed up are possible. We've implemented a lot of environments in Jax. We've done a lot of work to simplify algorithms. There's nothing harder than coming up with simple algorithms, and we've pushed the frontier of meta reinforcement learning. And we've also, so there's one more person who's joining right now, and I think we lost the sharing for a second. That's all fine. I think we're back. And this push the frontier of meta reinforcement learning, and everything is open source. So this is basically it's all there for you to explore. There's a really good question here, which is to what extent do these things translate to LLMs, to Gen AI, to the frontier? I've shown you some evidence that this is possible, and obviously we have to break out of the Jax box. And there's a lot more information at foersterlab.com and also on my Twitter handle at jfirst. Yeah, this was the first part of the talk. I think I want to basically use the rest of the time is about end-to-end automated AI scientist. This really is just a prompt engineering project to build end-to-end science. You've probably seen it on the social media or look it up. There's talks of this already online. So I think we skip this and we'll use the rest of the time for discussion and questions. Benjamin. I see a hand raised.
Hi, I'm clear.
Yeah, you're clear.
I was wondering if I want to search about RL at Hyperscale in the age of agentic LLMs. What kind of keywords should I search for? Or is there any leading paper that I can read?
I think I had the talk I gave today. I'm not sure if you were here for the entire talk, right? Papers I've covered in this talk are all the foundation of RL at the Hyperscale. Right? If you go to my website, foersterlab.com, you'll have links to all the papers that lay the foundation of the field. Okay? You're at the leading edge. You are like right now, all of you are at the leading edge now in this new paradigm of doing RL, right? And it's all linked out, it's all open source, it's all there. So I don't know what else to say, right? There's nothing stopping you, right? You can just go and get started. It's all linked out and open source, right? Foersterlab.com. It's all there. And we're not always perfect in updating. So you also look at the Google Scholar. I assume you can access that, right? You'll see new papers coming out from my lab. Like, this is it. We're writing history here. And you're welcome to join that. Any more questions?
I have a question, but before that, thanks for your awesome presentation. It gave me a lot of insights on how we can scale. But the question that is in my mind is about using RL in embodied agents, because based on what I understand from your talk, what we have to do is just make simulation that are accurate and can be run on GPU. My question is, what about we want to have a real physical interaction? Because how much that we can accurate our simulation, at the end, there are some noise and unpredicted things that happen in the physical device.
Look. I should have a slide for this, right? To be very clear, I'm not suggesting that we need to have perfect fidelity simulators of the real world. Ultimately, we will be learning in the real world and from real world data. However, I don't work on deploying existing algorithms onto real world problems. We are laying the foundations of the field of developing better and more robust learning algorithms. And this is something we confuse a lot. We pretend that engineering is science and science engineering, it's not. We pretend that the benchmark is the goal, but it's not. The goal of science is to understand the world better and to make it easier for others to solve new downstream problems more efficiently. And I'm saying if we're in the business of developing new algorithms, better algorithms that are more sample efficient, more robust in the real world, then we should be using the fastest simulation environments to do so robustly and efficiently to discover simple algorithms. And you have to understand this. If you don't understand that distinction between developing new algorithms and searching over algorithms, doing meta learning, and solving a specific real-world problem, right? Then you're setting yourself up for a long time of confusion. And again, it's that conceptual clarity, lucidity that I inspire all of you to pursue in life. Understand the world deeply and know what we're doing and why. And if you don't have this, you will be following the confusion that often exists in the field of machine learning, where people exactly confuse, the stepping stone with the target. Okay.
I see. Thank you.
Thank you for your question.
I have a question.
Please, Ali.
This framework of drifting function is really similar to what we have in LLM alignment, right? I think in that place, people are using KL and those things. So have you tried your new method of learning the drifting with LLM alignment? Or do you think it can be useful in that?
It's a very good idea. I think this is a very good idea. I was thinking about the same as going through this presentation. We have a paper and a submission that goes into this direction. It tries to deploy the same transfer that we do in LPO and DPO, but in the field of RLHF. Very good idea. And indeed, we have a paper under review which is exploring exactly this question, and we have very promising results there.
Yeah.
Very good point. Thank you. Okay. Nazir.
Hi again. Thank you for your insightful talk. It was amazing. Thanks. So I had two questions. One is that it's from the looks of it, when you talk about meta learning, naturally connects the concepts to bi-level optimization. I wanted to ask whether that theoretical side of this problem has been investigated and how do these connect conceptually?
Well, it doesn't connect. It is bi-level optimization.
It's exactly the bi-level optimization.
Of course, you have two levels, right?
Oh, okay. So
right? I mean, So this is two levels of optimization. We have this phi, right? And then we train given this phi, right? So it's a bit like a fully cooperative Stackelberg game, right? Where this RL agent now gets trained as a response to this. Yeah. It is bi-level. It's that's what this is. Again, we've done a lot of explorations I've done a lot of work on meta learning and on meta gradients and so on and so forth. In the end, for current paradigm, the only thing that has been effective is ES, not other meta gradient estimators.
Yeah. Okay, thank you. And another question. So can we just view it other than the eye of true optimizations and use some sort of LLM agent or a set of LLM agents to dictate the high level policy, something like that?
We've done work on this. I mean, there's a paper, if you look at DiscoPop. So again, this presentation is a little bit outdated now, a little bit, not hugely. We have a paper called DiscoPop that does exactly this, where we use the population of candidates. It's just a piece of code produced by LLMs, right? We've done exactly this. And you can also imagine that here, when we go and we distill this policy by hand, right, we can do this algorithmically also using LLMs, for example, right? So there are a lot of places here where LLMs can play a role, which is quite exciting.
Thank you. Thank you so much.
Wonderful. Thanks for the questions. Ali Moomin.
Hi again. Can you hear me?
Yeah, I can hear you. That's fine. Thank you.
Yeah. You said the role of agent RL in actually LLMs. You know, there's some theory that we can actually model LLMs as multi-armed bandits. My question is that do we need LLMs or can we go pure RL somehow? Are LLMs the building blocks?
Look, the future is fundamentally unpredictable. Okay. I think LLMs are here to stay. I think generality of intelligence has always been the pursuit of my research of decentralized democratic intelligence. That's why I started my PhD on learning communication protocols, because I thought that intelligence was connected to a multi-agent nature through language. And I think this question, LLMs will stay with us, right? However, LLMs currently are being mostly trained through imitation learning, and that bars the performance. So this question of open-endedness, systems that can generate their own training data, self-improve, and so on and so forth, using algorithms to find better algorithms, all of this, I think, will be the next wave of AI, and actually just much more efficient and better algorithms. So, I think LLMs here to stay, and also think RL is here to stay, and we're obviously experiencing a resurgence of interest in RL. Again, like you are, like all of you at the beginning of a tri-scientific trajectory, I assume. So be the future, right? Like, just because you're interested in RL and maybe you haven't been looking at LLMs, you didn't think that Gen AI was going to go so far, embrace it, right? But also understand what are the fundamental limitations and how can we move beyond this, right? It's one of the key questions, right? Which transfers are, transferable? How do we go from neural networks that have millions of parameters to those that have billions of parameters, right? Because they have very, very different scaling laws. Okay, I think I have time for one more question. Arash.
Can I ask mine? That's okay.
Please.
Okay. The reason that I'm interested in RL is really that I'm interested in how our brain works. And I don't really actually like the way that we integrate LLMs in the RL. And the way that I see our mind is we get from evolution some foundation models that we learn from them hierarchical abstractions in our cortex. And I just wanted to know that, your insight and your take on this, that how do you think? I don't think integrating LLMs in the way that we trained it is the right way to do. And I want to know how do you what do you think is the right way that we can train those foundation models that are like the ones that we get from the evolutionary process, in the multi-agent evolutionary process, develop them, and how we can learn on top of them is like.
Well, I think this is what I'm suggesting, right? I'm suggesting fast simulation environments where you can do loads of samples, can search over architectures, not too dissimilar from what evolution did to discover our, circuitries. And then you have various different levels of transfer, right? Do we transfer an agent's lifetime learnings? We transfer the learning algorithm, all of this, right? This is basically the simulation hypothesis. We can use large numbers of simulated experiences to effectively simulate the type of search meta-learning algorithms that evolution did on evolutionary timescales to search for efficient learners. So I think that's what I'm advocating for here.
Okay.
Awesome.
Thank you.
Can
I have a final question if you wanna?
Please.
Okay, but my final question is, what do you suggest us, because we are starting our career? What do you suggest us to do what areas we're gonna major on, what projects we go work on? If we're interested in the fundamentals quotient of intelligence and want to really work on fundamentals problems, what do you suggest us to go on and work on?
Look, like first off, understand the world deeply. That's the first step, right? The first step, get good foundations in math, statistics, physics, for example, things that train you to reason deeply about the world, right? And then go and find, some of the best people on the planet to work with. The thing that will make the biggest difference, most likely, is your ability of surrounding yourself with amazingly smart people. right? And then the barriers to entry to at this point, assuming you can get access to any types of GPUs, like 4090s from NVIDIA, for example, gaming stations, you can do state-of-the-art work. It's all there. Like there's nothing stopping you from pushing the frontiers of capabilities right now, right here. So, you know, be the change. Don't be like shy. Just go and, you know, think deeply, do good work, and seek out collaborations and positions of PhDs at the top institutes on the planet, right? And the best way to do this is to show absolute and utter academic excellence and the ability of executing on research. That's what, for example, I look for in my students. I look for people who are near the top of their class in one of the top universities on the planet, and that have got credible ideas and have executed on research projects, right? And all of this can be done nowadays anywhere on the planet.
Thank you. That was great advice.
Wonderful. In the long term, what matters most is your ability of understanding the world deeply. That's what we're here for. Okay? I'm going to stop sharing. Sorry?
How we can navigate the first question, understand the words deeply. How you navigate that?
You talk to smart people, you discuss, you think, right? You don't get too hooked up in the current papers, but you try to understand what the foundations of the universe are. What is intelligence? And develop the practical skill of iterating quickly.
Thank you.
Okay, I would like to thank you all for making this really fun and interactive, and wish you all the best. Obviously, you know, you can find my email on the website. Feel free to reach out, and I wish you all the very best of luck. Take care.
Thank you, Professor. It was really great honor, and thanks for accepting our invite.
Of course.
Have a great
rest of
rest of the day.
Bye.